the recording. Thank you everybody for coming. We are happy and proud to have with us today Arkadi Predtetchinski. He did his PhD studies in Maastricht University, where he is currently an associate professor. His areas of research are mainly the mathematical aspects of dynamic games, but he also has papers that are purely mathematics. And Arkadi, the stage is yours.
Gali, thank you so much for the invitation. I would like to start by perhaps by expressing my appreciation to the organizers for this wonderful sequence of seminars. I've been enjoying the talks tremendously, both junior and senior. So thank you so much for the awesome work. And I would like to thank all of you for coming today to this talk. Yeah, so the pure mathematics paper, one of them that we have is joint with Ville Suomala. So this work is a joint work with Janos, whom you all know very well, and with Ville Suomala, who you might or might not know. Ville is a fractal geometer who is also interested in the interaction between geometry and probability. And he is based in the wonderful city called Oulu in Finland. If you have a chance to visit it, do so. Okay, so I'm talking about perfect information games. What are these? Well, perfect information games are games where the players move in a certain sequence, and all the moves that the players made in the past are observed by everyone. Okay, so this perfect information. And in fact, we'll be looking at two-player zero-sum games. Now, two-player zero-sum perfect information games. Now, this is the class of games that's been studied really a lot from all kinds of perspectives, by descriptive subtheorists, by game theorists, by economists, by computer scientists, logicians. This is a very well-researched area. What we would like to bring in is perhaps a new perspective, a new viewpoint on such games. What we would like to offer is a probabilistic approach to perfect information games. Now, what do I mean by a probabilistic approach to perfect information games? Well, this approach roughly amounts to the following. We come up with a certain set of games. All games in our set are two-player zero-sum games of perfect information. And we also come up with a certain probability measure on top of this set. And that makes for a measurable space of games, okay? And the world that we envisage is the one where nature chooses a game from our set, and this choice is governed by the probability measure that we have on this space. Okay, so nature chooses a game, and once the game is chosen, it's given to the players who inspect it, who study it, and who think about how they are going to play this game. Okay. Now, all games in our set happen to have a value. That's because all games that we consider have bounded upper semi-continuous payoffs, and that guarantees that there's a value. And under our approach, the value of the game is a random variable, right? Because the game is random, so the value of the game is a random variable. And our task as researchers is then to study the distribution of the value. Okay, what does this mean? Well, we ask questions like these, for example. What is the probability that player one has a winning strategy? Okay, so let me rephrase it a little bit. Some games in our set have the property that player one has a winning strategy, others don't. So what is the measure of a set of games where player one has a winning strategy? Or another example of a question could be, is the probability that the value is at least k positive? Okay, so these are examples of the questions we could ask in this setup. So very roughly, this is what the paper is going to be about. And I hope that for the, I'll try to elaborate on all these aspects. But first, let me tell you about the existing literature. And for our convenience, I split the literature into 3 broad branches. So let me start with the first branch. This is, of course, the literature on perfect information games, which is very massive and huge. So I selected the works that are the most relevant to our research. In fact, the first one on the list, the one by Gale and Stewart, is very relevant. This is one of the first papers on infinite games with perfect information. And in that paper, considered are games with a closed winning set. And in fact, this is relevant because these are the type of games that we encompass in our setup. I mentioned Martin's Borel determinacy, even though we could do without, because this is such a milestone. This is really a landmark result, and not just in game theory, really not in all of distributed set theory. But this paper is about games that go beyond the scope of this paper. And I also would like to mention some works on games, perfect information games with semi-continuous payoffs. There are quite a few, with zero-sum or without zero-sum, 2-player or n-player games. These are relevant because all games that we consider have semi-continuous payoffs. Okay, so so as you can see, this is a very well researched area. I mentioned to you that the novelty of this paper is that we bring in a probabilistic approach to look at perfect information games. But this statement should be qualified because the probabilistic approach by itself is certainly no novelty in game theory. Right, so we have this branch of literature on random one-shot games. This is also a very rich and mature and very interesting area. Typically, one would consider, in the simplest setup, what you should imagine is a normal, that is a one-shot game, let's say a 2x2 game with 8 payoffs that are generated randomly from a certain probability distribution. And then one could ask questions like, is there a pure Nash equilibrium? What is the distribution of the number of Nash equilibria? What is the probability for the, say, best response dynamics to converge to a Nash equilibrium? Okay, you might still remember a wonderful talk by Marco a few, what was it, months ago, for the One World seminar series. In fact, Marco was presenting his recent paper on random one-shot games, which is now forthcoming in the MR. So this is the kind of literature I'm referring to here. However, all these are one-shot games, and we're doing extensive form games. So what about random extensive form games? Well, there isn't as much, but there is this very important paper by Ariely and Babichenko. They look at extensive form games of a fixed length. So their setup is going to be different from ours. And they generate the payoffs randomly, and the payoffs are attached to the terminal nodes of the game tree. So our study is going to be complementary to theirs, because as you will see, the measure on the set of games that we consider is quite different. Even more closely related to our work are these papers, and you will notice that they are not even published in game theory, and really these are not game theorists. Some of these people are probability theorists working on percolation, others are computer scientists, and really there's some interest here in adversarial versions of the percolation, of the classical percolation problem. So our contribution to this literature is twofold. I could say we really mix and combine different elements of different modeling techniques coming from different papers, resulting in a setup that is distinct from any of these, and in my opinion, somewhat more interesting for game theorists. In particular, we have a richer set of payoff functions that we allow for in our setup. Okay, so this was my review of the literature. Feel free to interrupt me, by the way, at any point. I'm happy to take questions. And this is the plan for the rest of the talk. So my ambition is to guide you through the two examples. And in fact, I'm going to spend quite some time on these two examples. Then I would like to explain to you how they fit into the general setup of the model. And then I'll be talking about the main results of the paper, but in fact, I might not spend a lot of time on the main results. Why? That's because these are technical results, and the juice and the benefit of these main results, they become apparent when you look at the corollaries. So if time permits, I'd like to talk about some of the corollaries to the main results. Examples. Okay, example one. Okay, so I'm talking about random perfect information games. And in this example, in particular, the game tree is going to be random. And it's going to be generated or constructed through a branching process. And the way it works is like this. So we start with the initial node over here. It's called the root of the tree. And this root of the tree is going to have a number of children, n. And this number could, in principle, be 0. And the probability for the root to have n children is this, 1 minus lambda times lambda in the power n. So for example, if I take lambda to be 0.9, then the root will have no children with probability of 10%, exactly 1 kid with the probability of 9%, and so on. So let's see. Okay, so the root turns out to have 3 children. And then each of these children are going to have kids of their own. And the number of children for each of these nodes is drawn just from the same geometric distribution, independently of each other and independently of what happened before, basically. Okay, so the first child of the root has 2 kids. The second child of the root, oops, okay, that child doesn't have any children, so it's a childless node. And the third child of the root has 3 kids of his own, and so on. This process continues like this, and we construct a game tree. Okay, so this is going to be a game tree. What are we missing? Well, in this game tree, we're missing who is controlling which node. So we have 2 players, and only 1 player will be active at a given node. So we have to assign the nodes to the players. And this we also do randomly. So we assign a node to either player 1 or to player 2. And the probability with which we assign a node to player 1 is denoted by Q. And we do so independently across the nodes and also independently of the way the tree had been constructed before. So everything's independent. All the random variables I introduced thus far are independent of each other in this example. The blue nodes are those assigned to player 1, and the red ones are assigned to player 2. Okay, ladies and gentlemen, so we have the game tree. We have the game tree, and now the players could play the game if only they knew what to do. So we're missing the payoff. Now, the payoffs in this example are very simple. Basically, player 1 wants to play forever. Player 1 doesn't like stop playing. Player 1 wants to continue playing forever. And well, this being a zero-sum game, player 2 wants to stop player 1. That is to say that the payoff is 1 if the play never reaches an end node. And the payoff is 0 if eventually an end node is reached, a childless node. All right, so we have a game. This is a game. Just to emphasize this point once again, once nature has constructed the game, it's been inspected by the two players. All of its elements are visible, and the players look at the entire realization of the play before they even start thinking about how to play it. So they're free to adjust their strategies to the game at hand. Now, the game has a value which could be 0 or 1. By the way, in this particular realization I have just presented to you, the value, you can see that the value is 0 because if player 2 chooses child number 3 at this node and child number 3 at this node, then no matter what player 1 does, the play eventually reaches an end node, right? So if player 1 goes up, then yeah, you can see that if either he has to continue to an end node or he has to give turn to player 2, but then player 2 terminates the game. And the same happens here. All right, so in this picture, the value is 0. But the question that we're asking is, what is the probability that the value is 0? Is it always 0, perhaps? Okay, or is there a positive probability that the value is 1? Okay, so here's the answer. Okay, what do you see here? Well, on the vertical axis, you see the thing we're interested in, the probability that the value is 0. That is to say, the probability that player 2 has a winning strategy. And the horizontal axis is the so-called player 1's activation probability. This is simply the probability with which player 1 is assigned to a node, and it's denoted by Q. And the most obvious feature of this graph is that it's not increasing. And this, of course, is very intuitive. The higher the probability for player 1 to be assigned to a node, the more nodes player 1 controls, the easier it is for player 1 to play the game, and the more likely it is that player 1 has a winning strategy, right? So it's really intuitive that this is a non-increasing function. However, what I find interesting here is this number over here, 0.1021. Now, the reason I find this number interesting is that if player 1's activation probability falls below this particular threshold, then the probability for the value to be 0 is 1. The value is 0 almost surely. So player 2 wins the game almost surely. Only if player 1's activation probability is above this threshold does player 1 have a chance of ever winning the game. Okay. So for this reason, we call this number critical activation probability, and we pay close attention to these critical activation probabilities in the paper. Sylvain. Okay, if you have a question, just interrupt me. Okay.
So, Arkadi, this is a function.
I believe that I'm
lambda,
done with
this value.
Marco?
Yes, this value QC, I assume, is a function of lambda.
Yeah, so lambda is fixed here at 0.9. And in fact, I'll show you the formula later on in the talk for QC as a function of lambda. Yes, it is.
Okay.
Yes. Okay, this was example 1.
What's
now we can go to.
Could you please elaborate on the meaning of the probability of extinction of the game tree?
Okay, so it is possible that the game tree is finite. If there are too many end nodes, the game tree could turn out to be finite. Now, if the game tree is finite, then of course player 2 has a winning strategy, right? Because player 2's objective is to end the game. And if the game tree is finite, then of course player 2 automatically wins and the value is 0. And the extinction of the game is the probability theorists' jargon, a term for the game tree to be finite. And it happens that the probability of this event is exactly 0.1111 in this example. So that means that the probability that the value is 0 is bounded below by this number.
Ah, okay, okay. That's not like it's something function, or it should not be. It's not a function of the activation probability. It's simply that it's plotted on the same graph.
It's not a function of the activation probability because
now I understand. Yeah. Okay.
Right. So if the activation probability is 1, then this number is exactly the probability that the value is 0. But if the activation probability is smaller than 1, then the probability that the value is 0 is higher than the extinction probability.
Okay.
Okay. Thanks.
Thanks.
Example 2 is a bit different. The game tree is no longer random. In fact, it's a complete n-ary tree. That means that every node has exactly n children. In my picture, it's a binary tree that's presented. Just as before, we assign every node of this binary tree to a player, either 1 or 2, and player 1 is assigned to a node with probability q. However, here there's something new. So we assign the so-called capacity to a node, and a capacity is just a number between 0 and 1, chosen in this example from a uniform distribution. And again, everything is done independently, so that the capacity is chosen independently across the nodes and also independently of the choice of the active players. Why do we need capacities? So they determine the payoffs. The payoff to player 1 is defined as the minimum capacity over the nodes that have been visited during the play. So for example, if this is the sequence of nodes that's being visited in the first 3 periods of the game, then you can see that the payoff is going to be not greater than 0.4 because we pass through a node with this capacity of 0.4. In fact, in this game that's pictured over here, you can see that the value is not greater than 0.4 because if player 2 chooses to go to the upper node here and also here, then no matter what player one does, eventually player one will have to pass through one of the nodes with a capacity of 0.4 or less, through this node or through this node or through this node. So that means that the value is bounded above by 0.4 in this example. Now the question we ask is, what is the probability that the value is smaller than 0.4 or smaller than 0.5 or whatever? Here's the answer. Okay, what do you see? So on the vertical axis, you see the probability that the value is smaller than 0.05. Now 0.05 is basically a very small number. It's like a 5% of the range of the payoffs. The payoffs range from 0 to 1. This is a very modest request that player one makes. Player one wants to know, okay, what's the probability that I get a value of smaller than 0.05? And as before, on the horizontal axis, you see player one's activation probability. And you see two lines. Why two? Well, because the blue line corresponds to the binary tree and the red line corresponds to the ternary tree. And just as before, both lines are non-increasing for exactly the same reason. Moreover, you see the same phenomenon occurring here in this example. Namely, we have critical activation probabilities. So let's look at the binary tree. If player one's activation probability falls below 0.53, then the value is going to be smaller than 0.05 with probability 1. And only if the activation probability of player Q is above this threshold is the probability that the value smaller than 0.05 positive. So for this reason, we call this number 0.53. We call it 0.05 critical activation probability. What is also interesting about this example is that if player one's activation probability Q is smaller than 1 over n, remember n is the number of children that the nodes have, then the value is 0 almost surely with probability 1. And this I find a little bit surprising and interesting because remember, the capacity is chosen from a uniform distribution between 0 and 1. So the probability that the capacity is 0 is 0. The fact that the value is 0 means that player 2 is able to drive the play through the nodes with a vanishingly small capacity. And that happens if player 1 controls too few nodes. So this was the presentation of the two examples. And if you have questions, then yeah, I think it's a good time to for me to take them. If not,
even if you know, the path over the tree were at random, with this model that you are talking about now, you would be looking at the minimum of a set of random variables at RIID with 0-1 distribution. So I don't see it as particularly surprising that that minimum is asymptotically 0. Of course, now here you have the added strategic element, but
yeah, you're right. You might be right. Of course, the key is the fact that both players choose the successor node.
Sure.
But the thing is that yeah, if player 1 doesn't have a lot of choice, then player 2 is able to kill him almost surely. I think we agree on this, Michael. All right, ladies and gentlemen. So let me then continue with the presentation of the model. And I would like to explain to you how these two examples fit. The primitive object, the one from which the model is constructed, is what we call a primitive distribution. It's a distribution. Distribution of what? It's a distribution of three random variables that we call iota, gamma, and psi, and you map them all. Iota is the active player, gamma is the capacity, and psi is the number of children. And you can take any joint distribution of these three variables you like. So going back to the two examples, how is this primitive distribution chosen in the two examples? Let me start with the second one because it's more obvious. Well, the psi, it's the number of children. It's not really random. It's equal to n with probability 1. Gamma is the capacity. It's uniform on 0, 1, and while iota and gamma are independent. Now, in example 1, the number of children has a geometric distribution. And what's interesting is this third bullet point, the way we choose gamma, the capacity. So look, the capacity is 1 as long as psi is positive. So as long as a node has at least one child. And the capacity is 0 if the node is childless. Okay. So this is how the capacity is chosen in example 1, and it produces exactly the payoff function that I announced, that the payoff to player 1 is 1 if the play never ends, if we never enter an end node. Okay, so this is a very nerdy slide because I'm explaining to you what a game is. And of course, you all know what a perfect information game is, but I have to do this because I've said that we construct a set of games. So a game consists of 3 elements: game tree, T, the assignment of the active player, and the assignment of a capacity to the nodes of the tree. Okay, and this is a game. How a game is played? Well, you've seen how the game is played. The players choose successively the nodes, and if we denote by H0, H1 the sequence of nodes successively visited in the course of the game, then the payoff to player 1 is defined to be the infimum of the capacity of the nodes that have been visited. Any such game has a value. The reason for that, by the way, is that this payoff function is upper semi-continuous and it's bounded, so there's a value. This is crucial. This is how the measure on the set of games is being set up. Somewhat informally, I could describe it to you like this. If omega is the set of games that I defined, then one can give in a very natural way a Polish topology on omega and define the measure on it in such a way that this triples the number of children, the active player, and the capacity. These triples are independently distributed across the nodes, and each has the distribution given by the primitive distribution. So these triples are IID across the nodes of the game tree, roughly speaking. Okay. I'm not going to guide you through this formal definition, but what I would like to do is to refer to Jacques Neveu, because we borrow the formalism from his work. From a formal point of view, a game is what probability theorists would call a marked tree. And people doing branching processes will probably recognize this reference. It's kind of standard in branching processes, I believe. Okay, so that brings me to the main results. And in fact, we have two, and probably I'll be very brief about the first one, and I'll elaborate on the second one a bit. Here's the first main result of the paper. Remember that V is the value and K is just a real number. And we're interested in this quantity, the probability for the value to be smaller than K. We prove that it is the smallest fixed point of the so-called value generating function fk, which I have not defined and maybe I will not. Okay, so this is really the technical technical engine of the paper, the CPU of the paper, if you like. The reason I'm not going to define the value generating function formally is because perhaps when you are buying a computer, you might not be necessarily interested in the CPU. You might be interested in the quality of the screen, of the audio, or the quality of the battery or the connectivity, but not necessarily in the CPU. So I'll be paying more attention to the implications of this result. However, I do want to explain to you what this value generating function does in somewhat informally. So the role of the value generating function in our analysis is a bit similar to the role of the probability generating function in the study of branching processes, and that explains the choice of the name, the VGF, the value generating function. So the value generating function reflects the usual recursions for the value. So what are these recursions? Well, if you look at a node, and if you want to compute the value of the gain of this node, then this value can be computed as the minimum of two things: the capacity at the given node, and either the largest or the smallest value over the node's children. You take the largest if it's the node controlled by player 1, and you take the smallest if it's the node controlled by player 2. And this, essentially, the value generating function, what it does, it maps the distribution of the value tomorrow to the distribution of the value today. Okay, that's the way it works. Okay, if you're not happy with this hand waving, do tell me so, and I'm going to click this button then. And that'll take me to a formal definition. But if you're okay with this, then I'd rather tell you more about our second result. Okay, so I'm player 1, and I'm interested in whether or not I have a chance of getting a value of at least k. The probability that the value is at least k, is it 0 or is it positive? Now, the theorem tells me that it's 0 exactly if these three conditions are satisfied. The first two are kind of trivial, and it's the third one which is really interesting. Now, I'll spend maybe 1 minute telling you why the first two are sort of trivial. Well, if the capacity is always at least greater than k, then of course the value is at least greater than k. So it's obvious that condition 1 is necessary. Condition 2 is also because if this probability were positive, then think about what would happen at the root of the tree. There would be a positive probability that the root of the tree has no children, psi is 0, but a capacity of at least k. Now, if the root of the tree has no children, it's a very simple game that terminates instantly, and the value is, of course, equal to the capacity at the root. So if that capacity is at least k, the value is at least k. So, okay, so condition 2 is kind of trivial as well. It's the third condition which is really interesting. So a certain quantity has to be small, and this quantity is a sum of two parts, two terms, the first of which is quite intuitive. We are looking at the expected number of children of a node but we only look at nodes that are controlled by player 1 and have a capacity of at least k. Now, I think it's pretty intuitive that this quantity should be relevant for the question of whether the value is at least k. It's also natural that the higher the expected number of children at such nodes, the more likely it is that this probability is positive. Interesting is the second term, which is the probability that a node has exactly one child, a capacity of at least k, and is controlled by player 2. And the reason that we have to add this term is this. Now, think about nodes having exactly one child. Now, from a strategic point of view, it doesn't matter who controls these nodes, right? So whether it's player 2 or player 1, there's no strategic choice at such nodes. And so we could also always reassign a node controlled by player 2 with one child to player 1, and nothing would change. And since such nodes are excluded from the first term, because here we only talk about nodes controlled by player 1, we have to add this event. We have to add this term, basically. So that's a bit of an intuition I have for you for this result. And this brings me to the corollaries to the main results. Again, if
I have a question.
Yeah.
I've got one question, if I may, about condition 2. So it seems like that's a condition one should impose on each node in the tree.
Gleb, yes, yeah, exactly right. Oops, it is imposed on every node of a tree because remember, P is a primitive distribution, and the capacity and the number of children are drawn from this distribution at every node, effectively. This is how the measure works. I took the root just as an example.
Mm-hmm. Makes sense. Thanks.
Okay, great. Corollary. So I have a list of 4. I'm not sure if I have the time to go through all 4, but that doesn't matter. Let me guide you through some of them, and you'll see what they're about. The first one is just a small observation, really. It's the fact that our second main result encompasses a classical criterion for the extinction of branching processes. Since there was a question about this word extinction, let me show you this corollary. Extinction refers simply to this event. Okay, this is the event of the extinction. It's the event that the game tree is finite. It's the extinction. So the extinction occurs with probability 1 exactly if there's a positive probability that a node has no children, and at the same time, the mean number of children is not greater than 1. Okay, this is well known. Okay, but I just want to point out that this characterization is embedded into our second main result. Let me talk about critical activation probabilities. I've already pointed out this phenomenon when talking about the examples. We've seen it twice. And here it's stated more generally. So, so we have the following. There exists a number denoted by QC of k with the following property. We'll look again at the event that the value is at least k, and we ask the question, is it positive or is it not? As player 1, I'm certainly interested in this kind of question. And the answer is that the probability that the value is at least k is positive if and only if player one's activation probability, Q, is above this number, QC of K, which is called a player one's K critical activation probability. So in other words, let me reverse this. If player one's activation probability falls below this threshold, QC of K, then the probability that the value is at least K is 0. That is to say, the value is smaller than K, almost surely. Now, we can actually compute the K critical activation probability, and we have a closed form expression for it. This falls under what I think are very natural and mild assumptions. The formula might look intransparent to you at a first glance, but if you stare at it for a couple of minutes, you will realize that actually it's been built from only 2 blocks. The first block is this over here. It's the expectation of the number of children, looking only at those where the capacity is at least K. And the second building block is this probability that a node has exactly 1 kid and a capacity of at least K. I think there was a question about whether in example 1, the critical activation probability is a function of, and yes, indeed it is. I think Marco had this question. So Marco, yes, this is player one's critical activation probability in example 1 as a function of lambda. In example 2, by the way, it's particularly simple. You can see that the larger is n, it's the number of, so in example 2, remember, we're talking about a complete n-ary tree. And the larger is n, the smaller is this critical activation probability, which is good news from the point of view of player one. That means that it's easier and easier for player one is to get a value of at least k. Okay, so this was my corollary too on the critical activation probability. Well, let me move on to corollary 3, which is related to example 2. In fact, see much of this picture before when I was talking about example 2. You've already seen this diagram. On the vertical axis, just as before, is the probability that the value is smaller than 0.05, and on the horizontal axis is player one activation probability Q. And you've seen two lines, the blue and the red. The blue one corresponds to the case of a binary tree when n is 2, and the red corresponds to the case of the ternary tree when n is 3. And you can see that, yeah, they cross each other. So there's not really a clear comparison maybe of what is better for player one. However, things get wonderfully simple when we go to the limit as n goes to infinity. And this black line over here represents the limit as n goes to infinity. So here's the formal statement. Don't bother reading this. What this says is the following, which is consider a sequence of models where at step n we have the complete n-ary tree. And what's important is that we generate the actual player and the capacity always from the same probability distribution. Okay, for all these members of the sequence, I and gamma, the player and the capacity, are drawn from the same probability distribution all the time. And we can compute the limit of the probability that the value is at least k as n goes to infinity. And in fact, the limit is wonderfully simple and very intuitive. It's just the probability for player 1 to be in control of a node and for the capacity at that node to be at least k. Okay, I find this very, very, very natural. All right, ladies and gentlemen, so that brings me, do interrupt me if you have a question, because this brings me to corollary 4, and that will probably consume the rest of the time I have, which is great. I didn't even count on getting that far, but I'm really happy to talk about the fourth corollary. If I were player 1, I would certainly be interested in knowing what happens here. Now, I talked to you a lot already about this event, that the value is at least k, but as player 1, I might actually be interested in knowing the probability that the value is at least k at a node controlled by player 1, that is controlled by me. And knowing the probability of this event, that the value is at least k, at nodes controlled by my opponent, player 2. So from player 1's point of view, at least, it seems very interesting to look at these conditional probabilities, that the value is at least k, conditional. Here I take the root of the tree as an example. So conditional on the root of the tree being controlled by player I, okay, either player 1 or player 2. Okay, what can we say about this? Well, we can say quite a bit, in fact. The first bullet point, I think, is extremely intuitive. Basically, what it says is that it's better to be at your own node. The value at player 1's nodes is higher than the value at player 2's nodes. Now, this statement formally is, of course, probabilistic. It's higher in the sense of the first-order stochastic dominance. So the distribution of the value of player 1's nodes first order stochastically dominates the distribution of the value of player 2's nodes. And it just means that beta 1 is always at least as large as beta 2 for any k. Okay, I think this is very intuitive, right? So this is what you would expect. Also, we know that both these numbers, and now I'm talking about the second bullet point here, are non-decreasing in Q. And this is also intuitive, right? The higher the activation probability of player 1, the better the value. Again, this statement is probabilistic, formally stated as a first-order stochastic dominance. As Q increases, we get a probability distribution that is superior in terms of first-order stochastic dominance. So we have established that it's better to be at your own node. Now you could ask, how much better is it? Is it a lot better? Is it marginally better? This is a difficult question to answer, but we could say something about this. So let's first look at the two examples. Well, what we can say about the relative benefit of being at your own node is this. Let's look at activation probabilities that are just above their critical thresholds, their critical levels. So that means let's look at situations when beta is just slightly positive. What is beta? Since I'm talking about example 1 here, beta is just the probability for player 1 to win. Okay. So when Q is hovering just above the critical activation probability, we're in a situation when beta, the probability for player 1 to win, is positive, but only barely. Okay, so as it turns out, in this situation, it's literally 100 times better to be at your own node. If you look at these numbers, then you will see that the ratio of beta 1 to beta 2 is 100. And this you can take as a proxy of how valuable, how beneficial it is to be at your own node. So the conditional probability for player 1 to have a winning strategy, given that the root of the tree is controlled by player 1, is 100 times higher than if the root of the tree is controlled by player 2. In example 2, it's actually infinitely better to be at your own node. And that's because as Q approaches its critical level, the conditional probability for the value to be at least K at player 2's nodes is negligible, okay, compared to the probability of the same event at player 1's nodes. Okay, so that's quite interesting. Okay, this was an illustration of the really final part of corollary 4. When we look at the ratios of beta 1 to beta and beta 2 to beta, we find that, first of all, they're well, the first one is non-increasing, while the second one non-increasing in player 1's activation probability. And we can actually compute these ratios or the limits of these ratios as the activation probability converges to its critical level. And somewhat miraculously, what we see in these two expressions are these same two building blocks we had seen before when talking about the critical activation probability. It's these same two building blocks from which the expression for the critical activation probability is built. Okay, the expectation of the number of children at nodes having a capacity of at least K, and the probability that a node has exactly one kid and a capacity of at least K. The second expression actually reveals something quite interesting. It basically says that the nodes controlled by player 2 contribute, so to speak, to the event that the value is at least K only if they have exactly one child. That is, only if player 2 has no strategic choice at those nodes. All right, Galit, please correct me if I'm wrong. I believe that my time is nearing extinction, which means that I would just like to mention that we have two applications that I didn't talk about. I'll spend maybe 40 seconds simply telling you what more or less these are about. Let me start with the second one, the avoidance game. So who is avoiding whom? It's player 1 avoiding player 2. In this second application, we consider the following scenario. Suppose player 1 is forbidden from taking actions that will take her to a node controlled by player 2, her opponent. Maybe because she's unwilling to take those actions or she's literally unable to. What payoff can she still secure at under this scenario? This is a game which is much harder for her to play. She marginalizes the role of player 2. She renders her opponent a dummy. She never concedes a turn to her opponent. It's a much harder game for her to play. So how well does she fare? This is application 2. Application 1 is what we call the conditional game, and the aim of this application is to say something about optimal strategies or k optimal strategies of player one. So for example, how many k optimal actions does player one have on average? Okay. How does this number depend on the activation probability of player one? All right, so let me move on to my last slide for today, which is certainly the most important slide of this presentation. You may forget everything I said until now, but you should remember this: two things. If one controls too few decision nodes, it might happen that one has no chance of winning the game. So if you want to have a positive chance of winning the game, make sure you control enough decision nodes. There might be a threshold. There might be a phase transition. Be sure to be above the threshold. The second take-home message that I have for the decision makers is this. The benefit of being in control of a decision node is the higher, the smaller the probability of winning. It's a little bit like the marginal decrease in returns on controlling a node. The smaller the probability of winning, the larger the benefit of being in control. Well, this concludes my talk. I think my time is up. I would like to thank you all very much for having me. It's been a pleasure, and thank you all for your attention.
Thank you, Arkadi. Do people have questions? Well, I have a question. Am I wrong in saying that when the probability of winning is very small, then a lot is about who controls the first node?
This is very interesting. Could be. Never thought about it in this way, Galit.
Okay.
It certainly is the case that yeah, if nodes don't have a lot of children, then of course it's important who controls a few initial nodes. Now, but just if the probability of winning itself is small, yeah, it could be. It could very much be, yes. So I'll have to think about it. This is quite a deep question. I'll have to think about this more carefully before I say anything stupid.
Okay, thank you. Thank you. More questions?
If I may, first of all, thank you a lot, Arkadi. This was a wonderful talk, very nice topic. In your second model, for the binary case, you saw that there is not only a phase transition, but there seems to be some sort of cutoff phenomenon. That, you know, that probability goes from 1 all the way down to you know, to very small values very fast. Is there? Yeah, here. If you stay in the class of binary trees, but you change the payoff function, do you think, you know, you'd get a similar phenomenon, or this is really related to the specific payoffs that you chose?
How would you like to change the payoff functions? The distribution of the capacity?
I'm asking you.
So, okay, so what we could do if we are to stay in the framework of this model, what we could do is change the distribution of the capacity. In this example, the capacity is chosen from a uniform distribution, but we could change that. And I think, yeah, the picture would change quite a bit depending on exactly how you choose the distribution of the capacity.
Actually, that was my second question. What if...
The second question, but not the first.
Okay, what if you choose a different distribution that's not necessarily uniform, but has a positive density at 0, like exponential? Do you think that there would be a big change?
Well, yeah, it seems to be, then there's even more reason for the value to be 0 almost surely, right? If there's an atom at 0.
No. The density. The density is positive at 0. So.
Yeah, we actually have a closed form solution for the binary tree and also for the ternary tree. And in fact, all I need to do is to plug in the exponential distribution into that expression. But I'm not fast enough to do so on the spot. So I'm certainly going to try this at home. But I think basically, you can get any, so maybe it's we can get any shape for this curve we want, as long as it's non-decreasing. That's my feeling right now, by adjusting the density or adjusting more generally the probability distribution of the capacity. So if you like to think about, I didn't show you this picture, but maybe you would like to think of the CDF of the value. So what's plotted here is the cumulative distribution function of the value. So the vertical axis is as before, but the horizontal axis is K, okay? And if I change the distribution of the capacity, then I think I can match more or less any CDF of the value. So something tells me that this is an onto function. Give me the distribution of the value you like, and I think, Marco, I will be able to construct a distribution of the capacity such that, well, we got exactly that distribution of the value you like in this model. That's my feeling right now.
Okay.
The dependence, yeah, in some ways it's quite simple. So for example, if the distribution of the capacity, number 1, first order stochastically dominates distribution number 2, the same will be true for the value. That's exactly what you can expect, right?
Thanks.
Yeah, thanks for the question. All questions are very deep.
Any more questions? Okay, then thank you, Arkadi, again. Very nice talk.
Thank you very much.
Okay.